Okay, I am recording now. Yeah, this is the talk about Ext and Tor. And also let me just share my whole screen so that you can see when I make annotations. Uh, okay, so just yeah, let me know when you can see my screen.
Looks like it's showing up now.
Okay, good.
I should see it.
Okay. Let me just check that the pen works. You can see these scribbles?
Yeah, scribbles show up too. They look very smooth.
Okay, good. Yeah, so anyway, as most, if not all of you know, I am giving a talk about Ext and Tor, which are two very important functors in many fields of mathematics. These slides were kind of, I mean, they're not last minute, but they're not fully complete, and I don't claim to be any expert on Ext and Tor, but by any means. So yeah, I just kind of felt like I wanted to give this talk because there hasn't been a talk for a while, and why not give the talk? It'll be fun anyway. So yeah, the plan is, okay, I'll give a little introduction, and then by the ingredients, what I mean is all of the homological algebra stuff which we will need to define Ext and Tor. So this will be homology, so what that is, hom and tensor products, those will be very important, and injective/projective modules. So those are the three ingredients that we need. Note that this section will not be a comprehensive guide to either homology, hom and tensor, or injective and projective modules. It will literally just be the definition followed by whatever property we might need for the rest of the talk. So it won't be kind of a comprehensive guide to any of these things. It'll just be some basic definitions so you know what I'm talking about later. Then derived functors, so we'll see that Ext and Tor will be defined in this section because they are both derived functors. Some computations. Now, computations plural is a bit misleading because I've only got one computation of each. Again, that's just because I didn't have time to write any more. And by applications, I will look a little bit at group co-homology. I won't take a deep look at all or anything. I'll just kind of point out that it's defined as Ext of something blah blah blah. And we will look at the universal coefficient theorem. And yeah, that will take us to the end of the talk. So, okay. That's pretty much covered the introduction as well. So yeah, well, I'll start off with the definition of homology. So firstly, we need to understand what a chain complex is. So a chain complex is just a sequence of modules. So all of these CNs, they're all modules. Let me make this pen a little bit thicker, yeah. So all of these are modules, and then we have homomorphisms that connect them, which are known as Dn. And note that this is decreasing, such that the composition of this and this module, map is 0. So in other words, this means that the image of the n plus 1th differential is a subset of the kernel of Dn, and so we're well within our rights to take this quotient here because it's well defined because we're allowed because of this relation here. And the point of taking this quotient is because when the homology is 0, so at this nth point here, if this homology was 0, this only happens when the image is equal to the kernel. And so basically homology can be thought of as measuring the exactness. Because of course this condition here that the image is equal to the kernel is exactness. And so, yeah, so homology is basically measuring how far away a chain complex is from being exact by taking this quotient here. So yeah, that's homology. And dually, so very similarly, we have cohomology, where this time we deal with a cochain complex, where this time the differentials are increasing rather than decreasing, and so we have this condition here, and so this time the image of dn, and note that sorry, this is a bit too thick now. Note that cochain complexes are denoted with superscripts and chain complexes are denoted with subscripts. And again, this condition here is the same thing as saying that the image of dn is a subset of the kernel of dn plus 1. So again, we're well within our rights to take this quotient here, which we call the cohomology of the cochain complex. And again, that's thought of as measuring the exactness, because of the same reasoning as I explained in the last slide. So yeah, that's cohomology and homology. So just to recap, whenever I say cohomology and homology, we will be dealing with a chain complex. So we'll be dealing with something that looks like this, and it will be the quotient here at this nth point, basically.
Can I ask a stupid question about the basic stuff before you go on?
Yeah.
I'm just thinking of you commented, you put a snippet in chat the other day about how someone was arguing that cohomology should be written as contra-homology or something like that to make an analogy with contravariant versus covariant vectors where the indices are upstairs or downstairs. I was just wondering, is there any deeper reason why one would call cohomology contra-homology or write the indices upstairs besides just convention? Like, was there any deeper argument for the terminology they were advocating there, or is it literally just words and you can say whatever you want?
Right. Yeah. I know what you're talking about. I think there was some slightly deeper context where that was said. The only reason I can think of right now that's more deep than just kind of the analogy would be when we do define right-derived functors later. We see that we can define right-derived functors as just like these contravariant versions or something like this, something like this. So it might be something to do with kind of the fact that you can define right-derived functors in this way, and maybe it's something like that. But
that statement seems parity symmetric. A left exact functor has right derived functors, and a right exact functor has left derived functors totally symmetrically. And it seems to me that neither of those statements prefers up versus down indices, right? I mean, is there any symmetry breaking why you would use up or down for one as opposed to the other, or is it just convention? I mean, it's fine if the answer is convention, but I'm just curious if there's a better reason.
I think I mean it is. I mean, to be fair, it's much more convenient to write this than that. I think that they have pretty much the same properties for this reason, but
okay.
yeah.
Tetra has an answer in the chat, which maybe I'll read for people who didn't read it. So Tetra is answering, it's a contravariant functor in geometric contexts, while homology is covariant. Okay, well, that I kind of buy if it's true. If it's true that there's any relationship between covariant and contravariant functors and covariance versus contravariance of vectors, then I would buy that connection to the notation. That's less clear, but okay. Maybe I
feel like they're only loosely related. The vector and the category.
That's probably true. Okay, I'm sorry for. I shouldn't derail Greg's talk. So maybe I'll stop.
If you wanna see the context, it was the footnote was in Rotman's book on homological algebra. So if you do some Control F magic, then you can tell us the answer. Anyway, if you really want to investigate that. But yeah, I don't recall the context in which that was said. I just thought it was kind of cool.
Speaking of kind of stupid questions,
Yeah.
are the values of n natural or are they integers?
Yeah, they're natural. The convention is that Ci is just 0 when I is less than 0.
Uh-huh.
So yeah, they're just natural.
Alright.
Okay, so yeah, so that was just cohomology and homology. I won't be giving any examples or anything like that. I'm just going to move straight on to the next ingredient, which is the Hom functor. So, this functor is very closely connected to Ext. So it makes sense to look at it. So the way that it's defined is, so if we're given some left R modules, X and Y, then Hom R, and often this subscript here is dropped when it's clear what the ring R is. So if you do see, so for example here I've dropped the subscript just because it's a bit inconvenient to write that out, and it's quite clear that we're working over just some arbitrary ring R. But anyway, yeah, it's defined as the set of all R module homomorphisms from X to Y, and of course, you know, it's not just a set. We can quickly make it into an abelian group, and we can consider it as a contravariant functor, as like so. Because for any map f from x to y, we get an induced map between Hom y m and Hom xm, which by just precomposing, just composing f with, by just mapping f to precomposition, by just mapping phi, some arbitrary map in Hom ym to precomposition with f, and that makes it into a functor, which you can check if you'd like. And also, we can also make it into a covariant functor if we instead were to consider it as a functor Hom m, and then we left this part here blank. But we'll see that when we're talking about Ext, you know, there's no real advantage to distinguishing either versus. It doesn't really matter for the sake of this talk which one we talk about, so I'll just talk about the contravariant functor from now on, basically. And yeah, so there's a very important property of the Hom functor, and that is that it's left exact. So what does that mean? Well, you know, one can ask oneself, what happens if I apply this Hom functor to an exact sequence? Does it preserve exact sequences? And the answer is almost. If we have a short exact sequence like so, then we get a short exact sequence like this, but the only problem is that this 0 here at the end is missing, because that condition there doesn't hold. So this property here is known as left exactness. Anyway, yeah, so, well, I will actually be proving this property of Hom, since it's quite a nice proof. So, okay. So firstly, let's prove exactness at this point here. So what we have to prove is that this map here is injective by basic properties of exact sequences. And so let's just assume that psi star of f is equal to psi star of g. And so we want to show that f is equal to g to show the injectiveness of psi star. So if we write this out explicitly, remember the definition of this induced map here. This would mean that f composed with psi of y is equal to g composed with psi of y for every single y and y. That's just the definition of two functions being equal. But the exactness of the original sequence, short exact sequence, implies that this psi here is surjective, and so so psi of y here, this actually covers the entire of z. And so basically we can rewrite this psi of y as just z, and so then we get g of z equals f of z for all z in z, which is the same thing as saying that f equals g, which is the same thing as saying that psi is injective. Okay, so, and yeah, that's what I've written out there. And so, for the exactness at this point here, we need that the kernel of this guy here is equal to the image of this guy here. And so we require that phi star of f is equal to 0 if and only if f is of the form, f is in the image of this guy, basically. And that follows from the exactness of the original sequence. So we've proven that HOM is left exact, which, just to recap, means that given this short exact sequence, we can obtain this short exact sequence by applying the HOM functor to it. Now, a question one might ask is, well, I kind of want to continue this sequence on. How can I do that? And the answer will lie in the Ext functor, and we will look at that later. So, yeah, that's one of the main motivations for studying the Ext functor, in fact. So, okay, let's look at the tensor product now. So, just to recap the ingredients, we've done cohomology, homology, and we've done the HOM functor now. So these are the ingredients that we've covered so far, and we've got 3 left. We've got tensor product and injective and projective modules. So there is an explicit way of defining the tensor product, but the equivalence relation you must modulo m times cross n by is kind of ugly, so I decided to give this kind of more smooth, if you like, definition. And that is the tensor product. So for a right R module M and a left R module N, we can form their tensor product, M tensor N, which is an abelian group. And what it is an abelian group, and together with a map, which sends Mn to M tensor N, such that for some homomorphism F, there's a unique map F tilde which makes this little triangle commute. And so the tensor product is also a functor because you can just map some map F to the identity tensor with F. So say we have some F between X and Y, then we can obtain a map between M tensor X and M tensor Y by just mapping M tensor X to M tensor F of X, like so. And it's a covariant functor. And even if we swap these around, so if we do this, and we make it into a functor in the obvious way, it will still be covariant. Okay, so firstly, we'll talk about some basic properties because this is a slightly more abstract definition than the definition of Hom, so we'll talk about some basic properties. So firstly, this map between M cross N and M tensor N, the elements of this guy here underneath this map generate the whole tensor product. That is, every single element can be written as a sum of these of elements of the form X tensor Y. So in order to compute tensor products, all you really need to do is look at elements of the form X tensor Y, and they'll tell you quite a bit about that. And here are some 3 other properties. I think that these relations here themselves are actually fully define the tensor products anyway, so I think these are the relations that you would need to define them. So firstly, it is distributive, so we can distribute the X like so. And the other way around too, so it's right and left distributive. And also, it commutes with this product here, with R times X and R times Y. So it commutes in that way.
Just to sharpen something you just said about whether this defines it, because I'm just thinking for intuition about the stupid vector space example, not even modules. So basically the example you said on the commutative diagram you gave on the previous slide is saying that the tensor product is defined by the statement that any bilinear map on the tensor product corresponds to a product of linear maps on the individual factors. That's this factorization statement. So is that not equivalent to the 3 things that you've written on the previous slide? So is it an if and only if, that if you have this unique homomorphism property in this slide, that's exactly equivalent to the 3 linearity properties that you've written in the last 3 bullet points on this slide? Or is there something additional you need to put in and they're not exactly equivalent?
No, I think you're right. I think this is a if and only if thing. So I think this is an alternate way of defining the tensor product, basically. But it's not immediately clear from the diagram, so I thought I'd add it in anyway. But yeah, I think it is the exact same thing, basically. Just
I think the generation thing is also a if and only thing. Like,
is it?
Because it is the smallest billion group that satisfies that factoring property.
Well, I don't think the factorization in the first bullet point is enough, right? Because this doesn't tell you how maps act on the basis elements, which are the tensor product. So the first guy I don't think is enough, but I think the linearity stuff might be equivalent to the diagram, if that's what you're saying.
Mm-hmm.
But I mean, yeah. I'm not sure if this is. I know pretty much for sure that these 3 definitely are kind of the same as the diagram. Not sure if this one is too, but yeah. Either way, it's true. So yeah.
I buy it. Good.
Yeah.
Yeah, it works out. It works out.
Yeah, exactly.
Just works.
Okay, and also the tensor product is right exact. So, for the Hom one, we were missing out a 0 over here, but now for the tensor product one, sorry, no, yeah, yeah, for the Hom one, if we were to write it the right way round, like this, we would be missing a 0 over here, but that's called left exactness, and for the tensor product, we're missing a 0 over here, basically. So that's right exactness. And the tensor product is right exact. And again, you might be wondering, well, can we continue this short exact sequence in some way? And the answer again lies in Tor, so we will be looking at that in further detail later. I will not be proving the right exactness of the tensor product, because I think that's a little bit more technical than proving the left exactness of the Hom functor, so I will just leave this as, just trust me, basically. This is right exact. It should also be noted that the tensor product doesn't preserve injections. So, as an example of this, if we consider this exact sequence here, where I is the inclusion, then obviously this here is an exact sequence. And by right exactness, this sequence here is also exact, so we can just tensor everybody by the integers mod 2. But this thing here is actually equal to 0, because if we're given some basis element A tensor Q, we have that A tensor Q is equal to A tensor 2Q over 2, which is equal to 2A tensor Q over 2, and 2A is equal to 0, and 0 tensor Q over 2 is equal to 0. And so, because this is equal to 0, and this guy here I believe is equal to the integers mod 2, this map here cannot be an injection, even though this one here was. So the tensor product does not preserve injections. That's just a note that I thought I would give. But yeah, okay. So, and hopefully that little example also has given a little bit of a better understanding as to how the tensor product works. But anyway, yeah. So, let's go back to the ingredients for a second. We have ticked off now, we've ticked off cohomology. I'll put the co in brackets so that we've covered cohomology, homology, Hom, and now we've covered the tensor product as well. So what we have left to do is we have projective and injective modules left. So let's start off by looking at projective modules. So we say that an R module P is projective if given R modules M and N and module homomorphisms F and G, as we can see on the diagram. Also, this F should be a P, where F is a surjection. Now, the reason that this thing here, this doesn't actually need to be on the diagram, but the only reason it's there is kind of it's neat to put it like that because this bottom row now is exact, and so that's kind of neat. But it does not need to be there. We only need that F is surjective. There exists, and this is not a unique module homomorphism, it's just a module homomorphism H, as you can see on the diagram, such that the whole thing commutes. And a theorem which I will not be proving, but is true, is that the following are equivalent. So either P is projective, as we just saw in this definition here, the Hom functor, the covariant version, is exact, or there exists an R module Q such that P direct sum Q is free. So these three are all equivalent, so I could have defined a projective module as any module such that it makes the thing exact, or I could have defined it in this way either. I don't think this one here will be too important for the talk, but it's good to know anyway. These two are the important ones for the talk.
Sorry, Greg, I'm sorry I keep interrupting, but I'm just, can I ask, you won't like this, but can I ask a question about how to morally think about this? Because I mean, I've written this definition and worked with this, but I'm just trying to think kind of like in your head, when like doing proofs, like how do you think about this projectivity property? Like the third of those equivalent conditions you've given me makes me think that, oh, kind of morally under the hood, one should think about this in some way kind of like a splitness property, the same way like in a short exact sequence, if you have a splitting, then you have some sort of, something is like a sum of other things or something like that. So like, is there like an intuitive way that you would suggest that we think about the property of projectivity that's analogous to that?
Well, I mean, I kind of like this second one the best when I'm just thinking about what a projective module is. When dealing with actual proofs using projective modules, it's usually this definition here that's the most useful because this map here is often important in the proofs. The fact that we can lift to a module M. The thing about the splitness, I think that if we have, now don't quote me on this, but I think that when we have an any short exact sequence like this, I think that this is always going to be split short exact sequence, where all of these are projective, of course. Now don't quote me on that, but I seem to recall that being the case. So I think that there is something to what you've said about the splitness. But just in general, when I think about projective modules, I think about this second property here. And when I'm doing proofs using injective modules, I mainly use this property here just because this lifting map can be quite important in most proofs. But yeah, I don't know if that answered your question, but yeah.
I think that's good. Also, Tetra gave a sort of orthogonal answer in the chat that says that maps out of projective modules factor through projections onto the target. So the factoring, okay, I kind of like that intuition about the factoring through picture, since that feels very kinetic to me. But I mean, I don't know, the splitness thing is nice as well, because I mean, I wanted a way to think about projective versus injective or something that was like I don't know, kind of had this intuition or something like that. So anyway, I don't know. I think that's good. Thank you.
Okay. And oh shit. And yeah. Something that's going to be of great importance to us is sorry. Something that's going to be of great importance to us in this talk is the idea of a projective resolution. And what it is an exact sequence of this form, such that each of these boys here are projective. And I believe that I should have added a 0 here. I think that the reason that I don't have that 0 is because this epsilon should be a surjection, I'm pretty sure. And this epsilon here is called an augmentation map. But yeah, so this is a projective resolution. It's an exact sequence that looks like this. And yeah, it will be very important when we're constructing derived functors. And an important result, I must say, an important result that I nearly forgot about, which we'll just take for granted, is that every single R module M admits a projective resolution. We can't just take that for granted if we were, if this was like research, but of course, this is just something that we're going to take for granted because I know that it's true. And okay, so just keep this definition in mind. When I say projective resolution of M, I mean all of these projective guys here, augmentation map, and exactness. Now, injectivity. Injectivity looks very similar to projectivity. Again, this 0 here is not necessary, it's just given because it makes this bottom row commute. But yeah, you don't actually need that 0 there. And yeah, so we say that E is injective if, for our modules M and N, we have an injective map F and a map G, such that there exists, again, not unique, just there exists a H such that this commutes, and this should not say E to N, I'm pretty sure this should say N to E, such that this diagram commutes. And similarly to projective modules, E is injective if and only if this is exact, so the contravariant version is exact. So remember that for projective modules, P is projective if and only if HOM P is exact, but this time E is injective if and only if the contravariant version is exact. So there is a sort of duality there between injective and projective modules. So yeah, that's another property that will be useful to us. And again, we'll take a look at injective resolutions, and this time we start off with M and go this way, such that each I is injective. And again, another property we'll take for granted is that every single module admits an injective resolution. So those are the ingredients that we have collected. We will need all of them for defining Tor and Ext. Again, that was not meant to be a comprehensive guide of any of them. It was just meant to, I was just giving some definitions so that you knew what I was talking about later on in the talk. And my throat is, what's the time? Okay, my throat is getting quite dry, so I'm just gonna grab some water and then I'll be back in like 5 minutes, 3 minutes. So yeah, that was just the first section. I'll be back in like 3 minutes, unless there's any questions immediately. Okay, I'll be back in like 3 minutes.
He's going to get water and then something after that?
He's been cutting out a lot.
Yeah, it was cutting out for me as well. But I heard something about water and then something mumbled after that, which I couldn't tell if the second part was important.
Okay. Water in hand, and I'm just gonna check if these pings are math talk related. No, they are not, so I will continue.
You're going to be very disappointed if you expect them to be math related.
It's good to be optimistic. Anyway, so that first section there was just collecting all of the different things that we needed in order to define derived functors and all of that stuff. Okay, so our motivation for studying derived functors is, well, recall what a left exact functor is. If we have a short exact sequence, it nearly preserves them. It just doesn't have this zero at the end. And in homological algebra especially, but often in kind of geometry and topology, etc., a short exact sequence naturally gives rise to a long exact sequence. And so we want a group of functors called right-derived functors, and again the motivation for left-derived functors is analogous, which are denoted in this way. And C and D are just arbitrary categories, although we will be working with modules this whole time. But this does work in pretty much any abelian category with enough projectives. Such that, firstly, we want that the zeroth derived functor is equal to f. And secondly, for any short exact sequence like this, we can obtain a long exact sequence, which has this part here, and then we have a map, a connecting map, which maps to R1 for f of a, and then so on and so forth. So what we're going to do now is construct them, and then we're going to define Tor and Ext with ease after that. Okay. So, a result that will be necessary for this is called the horseshoe lemma. The horseshoe lemma, and it's called the horseshoe lemma because this is kind of the shape of a horseshoe. What it states is, if we're given this diagram where the row here, the row is exact, and the columns, these are projective resolutions, then we have a projective resolution of A. So we have a projective resolution that looks like this, and such that the three columns form exact sequence of complexes. So we also have exact sequences going like this too. And this will exist. Now, I was going to prove this, but I ran out of time making the slides, and the idea is that this P0 is actually defined as the direct sum of both of these projective modules, and that fits together nicely and all of that, but I can't recall exactly how to prove it. But it is quite a satisfying diagram chase, so maybe if I have time after the talk, I'll add it to the slides before I share the slides to the server. But for now, we'll just take this lemma for granted. So, okay, now, we now are actually in a position to define derived functors, and I will show on this slide that the exact sequence condition does hold. Yeah, I did run out of time when I was writing these slides, so I didn't actually write a slide about it, but I think I am able, using the horseshoe lemma, to prove that the exactness holds. But anyway, how do we define them? And before I say, actually no, let me define them and then I'll say something that will be quite important to establish before we move on. In fact, necessary to establish, otherwise the whole thing doesn't make sense. But anyway, okay. So if we have a right exact functor f, and a projective resolution like so, then the left-derived functors of f are defined as the homology of this complex, which you form by taking a projective resolution, This yellow is kind of hard to see, so I'll change the color. So, taking this projective resolution, like so, and then we cut out the A, and then we apply F to everybody. So, then we're left with a complex FP0, FP1, blah 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 blah. Like so. And just taking the ith homology of this complex is the left-derived functor of A. Now, the important thing that I was banging on about a couple of seconds ago is this definition dependent on which projective resolution we pick? Because that would be a disaster, right? Because then, this would be ambiguous, the whole thing would just not be well defined at all. So, I will not be proving this, but I can, because it uses chain homotopy and I did not introduce that in the ingredients, but I can put your mind at ease, and I will tell you now that this definition does not depend on the projective resolution that we pick. And of course, the same thing holds for right exact functors. So if we choose, I think this should say not projective, injective resolution. If we choose an injective resolution like so, then we define the right derived functors of this left exact functor to be the cohomology of, and again, this this complex here.
Greg, can I ask, when you say it does not depend on the choice of, say, projective or injective resolution, is the statement that if you had chosen a different such resolution, then the result would be naturally isomorphic? Is that the statement?
Yeah, exactly. So if we were to choose a resolution like this, then if we were to do the same construction, we would get the same result, basically. Yeah. Because, of course, if that was not the case, then, it would be a disaster.
Okay, so the HIs are actually the same, independent of which P that you choose, but before defining the HI, if you just make the diagram where you extend to a long exact sequence with the LI, then that thing is naturally isomorphic to some other choice, I guess, is the statement. But then when you compute the HIs, then it doesn't care. That's the claim, I guess.
Yeah. So the only thing it depends on is this A. And similarly, right derived functors are defined in this way. And note that a left exact functor defines a right exact functor f op, which flips all the arrows and everything so that it becomes right exact, not left exact. And so one can define the right exact functors in this way, as I said earlier, like so. And the only reason I've pointed this out is so that when I prove, for example, the exact sequence property of the left-derived functor, then we don't need to prove it for the right-derived functors because we know that they have pretty analogous properties, basically, is the point of me pointing that out. Okay. Now, again, so this proof of the exact sequence condition, roughly at least, it goes as follows. So if we are given an exact sequence like this, then by the horseshoe lemma, we can construct, projective resolutions such that this sequence of complexes is exact, and so then we can apply our functor f and we can obtain another, and I think this also splits in this way as well. And anyway, so we can then apply our functor f, and we should basically in the end get an exact sequence, short exact sequence of complexes, like this. Which then, because a property of homology is that if we have a short exact sequence of complexes, that induces a long exact sequence in or normal homology. And so, of course, we get an exact sequence of which looks something like that. I think you know what I'm trying to draw out. But of course, the homology groups of these complexes are just the left-derived functors, and so in fact what we're getting here is an exact sequence which looks like that. And so that is roughly, of course it's not a precise proof, but basically what you do is you take initial short exact sequence, you use the horseshoe lemma to obtain yourself a new short exact sequence, but this time a short exact sequence of complexes. And now that you've obtained a short exact sequence of complexes, you're really in business, because those things do indeed induce a long exact sequence in homology, and of course you've defined your left exact functors precisely as the homology of these complexes. So it works out like that. Yeah, and alright, yeah, so yeah, that's what I wanted to say for that slide. Yeah, I'm just trying to think of I didn't prove this either, but why the is just this. I believe it has something to do with what happens when you chop off the A at the end. Because the original thing was exact, and so something like the kernel of this guy is equal to the image of some guy before, and so in the end when you compute the homology you will get A. But I don't have that precise argument written out, but it does turn out that when you do the left exact functor at A, you do indeed just get f of A, like so. Anyhow,
maybe I'll read, because Tetra had a question in the chat, which it was about 2 minutes ago, so I don't know if it's still relevant, but I just saw it now. But he asked, what are we verifying, and what is the quote exact sequence condition? I think that might be a slide or so back that we were checking. I don't know if.
Hold on, let me hold on. Yeah. Okay, wait. Let me just see.
Actually, the thing we were checking may have been what you were drawing with EpicPen, which may have unfortunately gone. But
what is the exact? Oh right. Oh. Okay, I know what you're talking about. Right. The exact. Yeah. So oh right. I should have pointed this out. Yeah. In our original motivation, we wanted this exact sequence here to be exact, basically. That was our kind of motivation for studying these things, and so I was verifying that the construction that I outlined does in fact satisfy our motivation for studying them. Yeah, that's yeah. I think that answers the question. Yeah. Okay, yeah. So that's what I was verifying there. And so yeah. So now that we've defined derived functors, Ext and Tor are just a special case. If we just, for convenience, define a functor g as being the Hom functor, then Ext is just the right derived functors of this Hom functor. Also, it should be noted that it doesn't matter if I were to define g of b, for example, as Hom a b, the Ext will stay the same. So it doesn't matter which functor we're talking about, the Ext will be the same. Same with the Tor functor as well. I think you can guess what the Tor functor will be at this point. The Tor functor is just the derived functors of the tensor product. And so yeah, now we've defined Ext and Tor. I did want this next section here to be slightly longer because this is kind of the main chunk of the understanding, but unfortunately, yeah, I just, yeah. Hopefully this one example at least does help. What we're going to be doing is we're going to be computing Ext and Tor of a finitely generated abelian group. And so these are groups of the form this. So blah, 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 blah. And by Ext, I mean XZ. So, yeah, I should have, oh, yeah. I should have included, yeah, so the ring here is important, of course. The ring here just corresponds to this boy here, and this ring here corresponds to that ring there. Again, I might omit the ring when I'm writing them out, but that's only when the ring should be somewhat clear what it is. So, again, what I'm talking about here is Ext with a little over the integers here. So whenever I say Ext, I mean over the integers, basically. So we're going to do, and another thing that I take for granted is that Ext and Tor do, in fact, preserve direct products, which I believe was the, I don't want to call it a thumbnail, but the picture that was used for the event on Discord by Furco was the property that Tor preserves direct sums, if I'm recalling correctly, but it does. So we can compute this in 3 stages, basically. Firstly, we're going to compute Ext like this, and then we're going to compute this. Also, we would need to compute this, but it's just trivial because the integers are projective, and if our first variable here is projective, then the whole thing is. And the intuition for that, of course, is that remember that something is projective if and only if it makes Hom of P something exact. And so the X things, which are supposed to be continuing this exact sequence, just become 0 because the sequence is already exact, basically. And so if you were to compute the homology, it would be 0 because there's already an exact sequence there. Oh dear. Yeah. So we only need to compute these 2 things. So let's do the first one. Okay, so we have to pick ourselves a projective resolution, and I did not mean to say the integers mod 2, I meant to say the integers mod n. And it's given by this. Now, the reason we can do, and this is multiplication by n, this 0 would go on forever, and this is exact, of course, and the integers are projective, so we're well within our rights to do this. And when we apply the Hom functor, we obtain an exact sequence, and this Hom is over the integers as well. And so we get an exact sequence which looks like this. And this again is multiplication by n. And so in the end, hold on, I'm just trying to Right, yeah, because I think it's the hold on. This is the image of this is equal to the kernel of that. Okay, yeah. So this map here is a surjection, and we can do. I'm pretty sure we can just do the Ext by one of the isomorphism theorems. I believe we can obtain this modulo the kernel of this map, which of course is. I'm sorry. Wait, what am I saying? X. There should be some isomorphism theorem here, which I'm pretty sure that it will give me this result. Although, might just be that the homology that we just compute the cohomology here, and that obtains the integers mod n. Yeah. The image of this is surjection. It might, yeah, it might just be the image of this guy. No. The image of this guy mod the kernel of this guy.
I think Tetra is trying to help you in chat. He says it's just because the kernel is the image at the second to last one.
The image. Right, yeah, so this is a surjection here. Right? Is this just is this just an isomorphism theorem that I'm forgetting? It should be, I'm pretty sure. This is
He's saying it's literally just C mod 2Z. The image is 2Z, he says.
Oh, is it? Why is
well,
that?
He's still typing, so you can maybe you can see what he's typing. Because if I repeat what he's saying, then it sounds like I'm taking credit for what he's saying.
Tetra is typing. Okay, so here's the first isomorphism theorem to the domain mod the kernel. But why is
So it was an isomorphism theorem, which is, I think, what you were saying.
Yeah. It feels like one of those. I just don't get why it's not. Why it's the integers mod 2 and why the image is not just n times the integers, because this map. This map here is multiplication by n. You're right. Yeah. Sorry. Yeah. No. That's all good. You helped me out there, so yeah, it's all good. Okay, so.
Oh yeah, you did have n equals 2 at the top for Z2, but then you went to Zn.
Right,
presumably you meant Zn
yeah,
right?
Sorry, yeah.
Good.
It's because I crossed that out, but then when I cleared it all again, that should say the integers mod n. But yeah, okay, yeah, thank you. So it was just an isomorphism theorem, by using the exactness of that sequence. And so we obtain that, in the end. Okay, so now let's do this one here. So again, we'll begin with this projected resolution. And now we'll apply HOM, but this time we'll apply HOM, not HOM this, but we'll apply HOM something that integers mod m this time. And so this time we get this exact sequence, like so. And in a similar way to last time, if you do the quotient and you cancel everything out, you should just obtain that x is equal to the integers mod d, where now d is the greatest common divisor. So for example, if these two were both, if n and m were both prime, so if we were dealing with something like this, then we would just be getting the integers, we would just be getting a trivial group. But if they were both the same thing, then we would be getting the group back itself. So yeah, this is the general case. And anyway, using these two results, i.e. this one here and this one, also the fact that x1z is trivial, if we use that, both of these results, in the end, we are able to just put all of these together in order to compute x of any finitely generated abelian group, which is pretty cool. So yeah, basically what we did here was we didn't even need to do any homology stuff. We just used the exact sequence property of the Ext functor and just any derived functor in general. And then we used the first isomorphism theorem. But we started off with this projective resolution. We applied HOM in order to obtain this exact sequence. And bongo bingo, and we obtain our result. Now, we'll do Tor, which again, Tor is trivial when either of the inputs are projective. And so both Tor of the integers of zz and Tor of the integers mod n z are both trivial, so the only thing we need to compute is this. So, let's do that. Oh, okay. So again, we start with the same projective resolution. Then, once we tensor with the integers mod m, we get this weird looking chain complex. And taking the homology groups, we'll be doing okay, let's take a moment to think about this. So the image of this is the kernel of that. So this one here is injection. I think, okay, so this is an injection, this is a surjection. This is multiplication by n.
By the way, Tetra's asking, don't we want an injective resolution, which I think is true because they're doing Tor here, right?
Oh yeah, that's true. Do want an.
Oh, wait, sorry, is that true? Or do I have it backwards?
I think we. We should need an injective resolution. I'm not sure why I've done a projective resolution here. It might be that. It might just be that there's some. there is some reason why I've done that. I'm just trying to think of what it is. Gosh, why have I done that? Yeah. It should be an injective. I agree, but I think that
I think I might have it backwards. Actually, don't you? I've already forgotten this. The definition it uses injective resolution for Ext and projective resolutions for Tor. So maybe you have it correct here. Actually,
I have. Oh right, yeah.
I'm just confirming on Wikipedia because I forgot this already. But indeed, I think it's according to Wikipedia, at least for Ext, you're using injective resolutions, and for Tor, you're using projective resolutions. So I think what you're doing is correct. I mean, Wikipedia is saying exactly what you're saying, which is that you should, if you're looking at T of A, you should tensor A with a projective resolution of B and take homology, which is exactly what you're saying to do there. So okay, maybe it's right. I'm sorry if I if I muddied the waters.
No, yeah. Yeah. So wait, is what I did with the Ext wrong then? Oh wait,
Can you go back?
yeah, because I used the projective resolution with, but to be fair, I didn't take the homology of this projective resolution, so it might be that for the Ext I just used the short exact sequence property, which we get from the definition of derived from just a general property of derived functors. Whereas for Tor, what I'm doing is taking the homology of a projective resolution, which is the definition of Tor. I think that might be why everything works out nicely.
Oh, yeah, that might have saved you. Yeah, but I mean, here, if you're taking homology in this second, the later example, then you might actually want it to be projective, as you say, right?
Yeah. So I mean, I don't actually take the homology in the Ext example. What I do in the Ext one is I use the fact that there's an exact sequence which looks like this because of the properties of derived functors, and then I use the first isomorphism theorem instead of taking the homology, or sorry, the homology
Take
of.
cohomology. For the X case, wouldn't you have, if you had done it the other way, instead of using this property, wouldn't you have taken cohomology for the X example?
Yeah, I would have. Yeah, I would have taken cohomology of some injective resolution, I believe.
Yeah. Okay. So that's what I thought. I was just confirming that I didn't have it backwards in my head. So if you did not do the trick, you would have said injective resolution and take cohomology for X, but you don't need to do that because you used the trick, so it didn't actually matter.
Yeah.
But in the Tor example, you're not using the trick. So indeed, you do need a projective resolution and take homology, which is exactly what you say to do. Okay.
Yeah. I think that's right. Yeah. I think that I don't know. It might just be that when we're working with the integers and the integers mod n, this particular projective resolution just helps us out in every case, no matter whether we're computing X or Tor. Because for X we have the trick, and for Tor we can just directly compute the cohomology. Oh, sorry, the homology. And indeed, when you do the homology, we get the same thing as X. So this is also equal to X, and that's just a coincidence. I'm pretty sure. But it is indeed the same thing as Ext of the integers mod m.
While I'm interrupting you, I don't know if you gave this interpretation for kind of where the names come from. That Tor, since you're tensoring, is picking out some sort of torsion subgroup for Tor1, and Ext is classifying extensions. But here in the integer case, maybe you can comment, since it's kind of a nice interpretation, for the relationship with the torsion subgroup. So because here you have C and Cn, and it's the D is the M comma N or something. So do you want to comment a little bit on the relation with the torsion subgroup and extensions for Tor1 and Ext1?
Right, yeah. Yeah, Ext1 is classifying all of the extensions, I believe. Or, and Tor1 is a torsion subgroup, is some sort of torsion subgroup, which is where they get their names from, of course. Ext1 is just classifying all the extensions between A and B. And what do you know what particular torsion subgroup Tor1 of A B would be? Because for abelian groups A and B, this is always a torsion subgroup, but
Yeah, isn't it? Well, okay, I forget the the exact statement because I was hoping you would remind me, but it's something like for abelian groups that Tor one. Well, there's just one torsion subgroup, right? It's the subgroup of an abelian group that has all the finite order elements, right? So it's how does it work in this case with Zm and Zn? It should be something like, since D is D should be how does it work or something? Because morally ZD should be like a torsion subgroup because of this number theoretic statement that it should have finite order in Zm and Zn or something like that. I forget exactly what the statement is here.
yeah, but it definitely the name definitely comes from the fact, look at that, Tor1 of two abelian groups does yield a torsion subgroup.
Sorry, D here, you already said it. D is what the
It's the greatest
least
common divisor.
greatest common divisor. Okay, so let's do something stupid. If it were like 6 and 9, so it's 3, Z3, C3. So those things are supposed to have finite order in both. Oh, I guess it's kind of stupid here because they're finite, so everything's going to have finite order. Okay. Yeah. Okay. I'm not going to be able to say it precisely, I guess, but
Yeah, I'll look it up. I mean, afterwards. I mean, there's not much left of the talk anyway. We can look it up afterwards anyway. But yeah, it is definitely something. It's definitely because it is equal to some torsion subgroup, and the Ext comes from classifying extensions. Yeah, those I should have said that before, but yeah, that is where those names come from. Okay, yeah. Speaking of classifying extensions, group cohomology is one place is a special case of Ext. So group cohomology, what it actually does is it classifies central extensions of groups. So the second group cohomology of GM is in bijection with the set of all central extensions of G by M. But this isn't a general definition for HI of GA, and it turns out that actually what these things are is the right derived functor of what these things are called invariants, and it's the right derived functor of these things, but the catch is that these things are isomorphic to a certain Hom group, and so essentially this group cohomology, which classifies the set of all central extensions and so on and so forth, has some certain nice properties in other fields as well, but whatever. It is defined as this certain Ext group here. It's this special case of Ext, which is a nice, yeah. But yeah, so that's just a little application. I mean, I don't want to go into too much detail because I don't know any detail, but that is a special case where Ext is being used elsewhere outside of homological algebra. Again, if you want to learn more about that, then look up group cohomology. I'm sure there'll be various resources on that. And similarly, group homology is defined as a certain Tor. Yeah, I don't actually know much about group homology, but it is a special case of the Tor functor, and so I thought, it might as well be useful to point that out just in case it piques your interest or something like that. But that is an application, a special case of Ext and Tor is group cohomology and group homology. Now, another place where it pops up is in algebraic topology when we're talking about the universal coefficient theorem, which is, I forgot to add the zeros on either side of this. But yeah, the universal coefficient theorem is basically saying, so when you're taking cohomology with coefficients in some group G, you do the chain complex like this, and then you tensor it with G, and you take the homology of that instead. Now, the universal coefficient theorem is basically measuring to what extent this statement fails. Like this. Because this is not true. This is not true. But by how much? Well, Tor to the rescue, basically. HP of X tensor G is in fact isomorphic to this guy, as long as you add some junk, and this junk is precisely Tor of our HP minus 1 X G. And this now is isomorphic to HP of xg. And the idea of the universal coefficient theorem for homology is, if we know the integral homology, then using Tor, and by the way, Tor is short for just Tor1. I should have pointed out earlier, but Tor is just Tor1, and Ext is just Ext1, if that ever comes up as well. But anyway, the idea for universal coefficient theorem is, if we know the integral homology, can we then obtain cohomology with coefficients in some other group G? And if we're able to compute this thing here, then the answer is yes, basically. So that's another application of Tor. That is one way to compute the cohomology of real projective space. Sorry, homology of real projective space with coefficients in the integers mod 2, for example. And in fact, that is nearly what the meme demands. Right, yeah, this is the all greatly awaited thing. Now, let's just decode this. So firstly, grape is equal to 1. Cookie is equal to 2. So burger, this thing here, is the integers mod 2. This here is just the cohomology ring of RPN with coefficients in the integers mod 2. Now, this thing here, banana is Ext, pizza is hom, and this sequence is not only exact, this is split exact. That is, we have that this guy here is isomorphic to the direct product of this chunky guy here with X and stuff, and this guy here, this hom functor here. This is a special case of the universal coefficient theorem for cohomology. But this statement here is exactly what the meme tells us. So we compute it. And so when I is between 0 and n, we obtain this. And this is isomorphic to the integers mod 2. and using machinery, and this machinery here I believe is stuff like the cat product and the cut product. Once you have obtained this information, you can get the cohomology ring, which is precisely this guy here. Now, yeah, and that is a prime example of, well, this is actually interesting, because this is not the universal coefficient theorem for cohomology. This is something saying, well, we know the homology of this guy in some coefficients. Now, can we obtain the cohomology of that same guy with the same coefficients? And the answer lies within Ext and Hom, basically, in this split exact sequence here. And so we've used the homology of RPN in order to obtain the cohomology of RPN, and then we kind of cheated and we just kind of said, oh well, we know that this is the result, and it kind of agrees with what we've obtained earlier, so there we go. And yeah, that is the last thing that I do in the talk. Thanks for listening, if you're still awake. And yeah, I mean, it wasn't my finest talk, I would say, but hopefully you kind of learnt something or other, and you know, got a little bit, at least a vague idea of what the hell Ext and Tor are. And yeah, I'm just gonna turn off OBS and then we can discuss or whatever. Yeah.